So it seems here that everybody knows Jessica, but I think she does deserve a formal introduction as uh, too many affiliations. A professor in mathematical and computer science department, mechanical and industrial engineering, computer science department.
Go.
Those are her formal affiliations. I think more importantly is director of the Continuum Robotics Laboratory, which has exactly the same acronym as my lab. So we're both CRL. It was nice when we had a joint paper together. And she used to direct the Robotics Institute, and now she's an associate director. Is that correct?
Mhm.
I won't say all the numerous prizes she's gotten throughout the years because it's going to take most of the hour. I think the most impressive one is that she was in the top 40 under 40, but not once and not twice, but three times in a row, kind of taking too much space for all the other young people until they get older, and elected
And
one
then
of
I turned
the.
40.
And then she turned 40, so she can take more space. Lucky for the rest of the researchers. Uh, she does awesome work. I can tell that both as someone in the community and as a direct collaborator. What I really admire is uh, the effort to push forward a field. Uh, so I mentioned that she directs the Continuum Robotics Laboratory, but also she's trying to democratize this whole field and make it more accessible. This includes a blog with these snippets of information about different aspects of continuum robotics, which I had the pleasure of contributing a bit, but it has all these different aspects from algorithmic parts, the mechanical design. In this project, there's open source hardware actuation models, software visualization tools. So really making this field more and more accessible, which in my mind is admirable. I'm super excited for this talk. I had the pleasure of working with Jessica on a personal level, and she's an awesome collaborator, especially because she's so fun to work with. So that's on a personal note, and I'm excited for the talk. So without further ado, the stage is yours.
Thank you so much, Oren. Yeah, thank you for inviting me. It's quite an honor and a pleasure to talk to you this morning or this afternoon. I've known Oren, I think, since the pandemic. I think Oren reached out when I gave a keynote at ICRA virtually, and made a call to the community. We need better motion planning. And then, yeah, a wonderful collaboration started, and that's been quite a pleasure. And equally, it's fun to work with Oren, but you know that. Okay, let me share my screen. Does that look okay on your end?
Mhm.
Excellent. Okay, then I'm going to kick us off. I'm going to talk about physical and computational intelligence in continuum robotics today. And as we are from different disciplines in this talk as well, I'm going to talk about both sides of my research, which is both on the physical side. We are building and designing robots. Even though I'm a computer scientist by training, I did quite some extensive postdoctoral studies at Vanderbilt University to also learn about mechanical design, because as of to date, it is really hard to buy a continuum robot. So we had to kind of learn how to do it ourselves. And then we also do the computational aspects. All right, but before we start with continuum robots, I want to talk about industrial robot arms, because these are really the workhorses of modern automation. They are positioning themselves with sub-millimeter accuracy. They are repeating thousands and thousands of cycles per hour without any fatigue. So they operate in these highly structured environments. Every bolt, every panel, every welding seam is exactly where it's expected to be. So I'd argue that motion planning and control are largely solved for these type of applications to date, because the world is mostly rigid, it's deterministic, and it's fully known. At the same time, these robots are usually fully and heavily caged, so there's no uncertainty. Any deviation, any uncertainty, any contact with the unexpected would pretty much cause the whole system to halt. Now, in the past couple decades, we have also seen robots moving closer to humans. There is the counterpart of these traditional serial robot arms that are equipped with much more sensors, force torque sensors in every joint, and they have been termed collaborative robots, so they can do repetitive tasks closer to humans. And I guess nowadays we also see humanoid robots everywhere in tech demos, in news headlines, in investor decks. There's true excitement and real money going into the idea of building this general purpose robot that can walk into a warehouse or factory, take over manual labor, or if we see these recent, I guess, Tai Chi competitive motions of the Unitree, is quite remarkable and an appealing vision if we look at these robots pretty much moving like humans to date. And so a drop-in replacement for human workers is really appealing. They could use tools and spaces as they are with no redesign needed as opposed to these prior generation of industrial robots. But most of what we see today is still tightly scripted, carefully tuned, and far from robust in unconstrained environments. What is often missing is manipulation. When you see these videos, there's no real true physical interaction with any cluttered, deformable, or delicate objects, which is where most robots struggle. And while walking is hard and touching the world with skill, like grasping, peeling, threading, assembling, is even harder. So when we look at this variety of tasks, despite the humanoid hype, we still don't have robots that can reliably do most of the things we see here. They cannot operate in unstructured environment very well, and if they do, it needs extensive setup and extensive tuning. So these are pretty much everyday tasks that we take for granted, like peeling an apple, threading a needle, flipping a pancake. So robots can weld cars, they can do backflips, they can do Tai Chi, but so why can't they button a shirt or get a container from deep within a cupboard? Well, each of these tasks pretty much require subtle control of contact, friction, compliance. We require real-time feedback from both vision and touch. And it's not just about the grasping itself, but it's also about interacting with objects that are deformable, cluttered, fragile, partially occluded. So notice that many of these tasks also involve the environment in essential ways. It's like bracing against a surface, sliding along an edge, pushing other objects aside to gain access. And this is the real frontier in robotics to date. It's not walking or balancing, but pretty much mastering these messy, contact-rich, dynamic physical world that humans navigate in with ease. And recent research is promising that, I'm not telling you many different things, but approaches like imitation learning and foundation models are really showing that large-scale data and pre-trained representations can really help close that gap eventually. But generalization, safety, physical grounding pretty much remain major open challenges, especially when contact dynamics and environmental variability come into play. However, in my research, I'm taking a little bit of a different angle because so far, most of robotics assumes rigid bodies, discrete joints, point contacts. So even as we try to scale learning and control. But what we do, we are kind of reimagining the robot body itself. We're not seeing it as an articulated body with rigid links and joints, but pretty much as a soft, continuous structure that can bend, twist, wrap, and adapt physically to its environment. And this is the direction that the Continuum Robotics Lab that I'm directing is taking. So we're exploring soft and continuum robots that are inherently compliant, shape adaptive, capable of different types of physical intelligence. And that, in a sense, makes manipulation even harder because the body itself is infinite dimensional. Shape sensing is only indirect and control is underactuated. So usually also a highly nonlinear problem that we're facing. But at the same time, these robot bodies offer new capabilities. They inherently offer safe and adaptive multifunctional interactions in confined and highly unstructured environments. So continuum robots could conform to their environment. They can use their body for interaction and open up new manipulation in constrained, cluttered spaces. Now, I want to give you a few examples because here we're really leaving these typical human tasks, but we're looking at really hard tasks. For example, on the left-hand side, you see a few examples of regions within the human body that could be accessed minimally invasively through a small incision or a natural orifice. For example, up here, we see the pituitary gland. That's a gland in the center of our brain that produces a lot of our hormones. And many people, 1 in 5 actually, develop a often benign tumor at the site, and some need surgery. And so you could actually enter through the nose and remove this tumor if you had a tool that's small enough. Similarly to lung biopsy, envision if you had a suspicious tissue within the lung, we could go through the airway, through the bronchi, and move all the way down here to take a biopsy to see if the tissue requires any further intervention. Same with stroke. On the other side, so on the industrial side, what I'm showcasing here is all those tasks that really are characterized by limited accessibility, contact-rich applications, and very constrained environments like complex piping systems in chemical industry, which require maintenance and inspection, or all sorts of turbomachinery. I'm showing here, this is a jet engine that needs regular inspection, but you could also think of turbines in hydroelectric power generation plants or steam turbines that regularly need to be visually inspected and eventually require smaller repairs. So that's the kind of applications we're targeting with Continuum robots. And to give a formal definition for those that maybe haven't heard of a Continuum robot before, to differentiate from other robot bodies, a Continuum robot is an actuatable structure whose constitutive materials form curves with continuous tangent vectors at the mathematical description. So usually we have one dimension that is much longer than the other two, which makes it this like continuous appearing shape. And then Continuum robots can bend, often extend and contract, and sometimes twist along any point along their structure. So these are the so-called motion primitives that we try to create in a Continuum robot. Now, working on Continuum robots is difficult because the design space to achieve this continuous bending and compliance is actually quite large. But at the same time, as mechanical engineers, the designing robots with non-rigid elements is actually still quite unfamiliar. Most of the design tools are made for rigid materials. And so we often take inspiration from the animal kingdom to see, well, how are these complex tentacles, elephant trunks, or worms operated in a sense. Another challenge we're facing is the curse of dimensionality. As I mentioned earlier, Continuum robots have a kind of indefinite ability to move. And so the standard methods in robotics for kinematics, dynamics, motion planning, perception, and control usually assume these discrete joint robot architectures, which make the transferability sometimes questionable. Some methods work, some don't. So there's quite a challenge here. And lastly, from a control standpoint, we only have finite control over these bodies. Even though they have theoretically infinite degrees of freedom, we rely on a finite set of actuators. So we need to approximate the continuous shapes with some limited inputs. And that's both challenging from a control, but also from a design perspective. So to get a better idea of what we're doing in the Continuum Robotics Lab, we're kind of doing research on two sides of things. We tackle intelligence in robotics, both from an embodied and from a computational standpoint. On the one side, we explore physical intelligence by designing soft and continuum robot bodies that can passively adapt, exploit contact, interact safely and effectively with the environment. And as those designs are typically compliant, they also encode some sort of intelligence in their morphology and material behavior. And then on the other side, as the computer scientist and myself, we also tackle computational intelligence. We develop algorithms for state estimation, for motion planning, for control that allow us to predict, sense, and eventually act under uncertainty. And it is really this intersection of these two domains, the embodiment and the computation, that I believe will make the next generation of intelligent continuum robots emerge. And in the talk today, I'm going to talk to both sides. I will start us off with talking about physical intelligence, talking about how we explore the design space, look at different robot embodiments, and how we can achieve adaptable stiffness and motion capabilities. And then in the second half of the talk, I'm going to address the computational intelligence side of things. On this slide, I'm showcasing robots that have been in the continuum and soft robotics community. A few of them are ours, but many are from all these amazing researchers worldwide in this, I would argue, still niche robotics research area. So here we can appreciate all these different embodiments. There are different types. We see robots that have intrinsic actuation, mostly fluidic. So it's fluidic elastomer actuators, pneumatic artificial muscles, eversion-based or vine robots. And you see those are really on the soft side of continuum robots, as they're mostly made from elastomers, silicones, and so on. And then there are extrinsically actuated continuum robots, meaning that the mean of actuation is not within the body like a fluid, but it is extrinsic, so external to the manipulator. That's how we can achieve even smaller diameters. And these are typically driven by tendons. We see an example here from this is from EPFL. This is a robot that we built. This is an early version of a spring-based continuum robot where you can also, I think if you look closely and your Zoom connection is good, you can probably also tell there's cables running through that you can pull on the back end to produce some bending. And so this just gives you an idea about the universe of continuum robots that exist. In my lab, we mostly focus on tendon-driven continuum robots, as we believe this is the most versatile type of design. This is one robot that we have built a couple of years ago in-house. It's a 7 mm diameter robot. It has 3 bending segments. You can tell them apart. If you look closely, there are these little knots where the tendons attach to the tendon routing discs. These are usually made from metal. And then in the center, we have a core structure. These are nitinol tubes that are super elastic and can withstand strains up to 8%. So we can achieve quite a range of bending motions. And with 3 bending segments and then 3 tendons per segment to induce spatial bending, we can get this like tentacle-like motion behavior. And then more recently, Jimmy up here, a PhD student in his 3rd year currently in my lab, he is building I guess an adaptation of a tendon-driven continuum robot by using these thicker routing discs and these universal joints. And with that, he has built this system that can integrate nicely with a collaborative robot. So you can use a regular style robot to position the continuum robot, and then the continuum robot could move into a cluttered environment or workspace. And here he's just showcasing teleoperation of both robots. One thing that we often try to hide, but explicitly don't do so here, is that our continuum robots are typically very small, but the actuation portion is still considerably bigger. That's something that many videos do not necessarily showcase. That's something that needs to be worked on to miniaturize these actuation units. But at the same time, they usually stay outside of cluttered environments, so it's not that big of a deal. You might wonder why am I showing this universal jointed tendon-driven continuum robot, and that comes now because with this robot we can also showcase this physical intelligence. So this is a single segment which now has a very special type of tendon routing. It's helical routing. And so by using just 3 actuators down here, these are 3 servo motors, and we can induce this helical rolling gait, and this robot is able to crawl up this tube by the pure morphology of things. So it's pretty much helically screwing up its way through this pipe. It's 20 times faster, so it's actually really slow in reality, but you could think about inspection being possible this way. We can also slant the tube, and so it can also move upward. And when we think back of this chemical piping industry, we may be able to use a robot just with this physical intelligence in its morphology to do some of the inspection task without much compute. So we can pretty much offload this into the body. Another thing I wanted to showcase today is some work by Puspita Devi. She's up here. She just finished her master's and is now a robotics engineer in my lab. And she did design these modular units, which is quite exciting, to compose a tendon-driven continuum robot. So she looked at different pre-programmable stiffness modules, a module with low stiffness, medium stiffness, high stiffness. And then she parameterized the design such that if we have application requirements, like this is how far we have to reach in an environment, this is the type of curvatures or bending motions we need to perform, this is the kind of stiffness we would need for this length of a robot to withstand gravity and hold its own weight, then she can come up with a composition of these modules. And as we can rapid prototype them quite quickly in various sizes and forms, it allows us then to quickly assemble custom continuum robots for a variety of tasks. So here we see the assembly process. It's quick and easy. And then we would test the robot. This is a manual testing setup, so there's no robotization here. These are just two manual input devices, which are essentially pulling and releasing tendons in this system. So this is work we presented last year at RoboSoft. And then this year, Puspita took this further and created a prototype that can be used for aircraft wing inspection in a mock setup. This is a scaled down version of a Cessna aircraft wing. And usually the inside, which holds the kerosene, needs to be inspected visually. So all these different areas that we marked here with this pattern need to be inspected visually to make sure there's no cracks, nothing faulty. And so the robot was designed based on the requirements of this task, the different bending angles and the depth the robot has to reach. And then she built the system, and it is manually operated by a user in using teleoperation, regular joint space and task space controllers. And then the operator is using this tip camera monitor, watching out of the tip of the robot as they're navigating through the environment. And then there's a bunch of other things we can do in order to achieve physical intelligence. We can build sheaths that can adapt the stiffness of the robot. We can build them very lightweight from origami style patterns. We can join continuum robots together eventually to give them higher payloads, because that's one of the downsides of having a lightweight compliant structure, that the payload and I guess ability to exert forces on the environment is theoretically limited. So we need to be quite smart about how we operate these robots. So one idea is to have them join together to become stronger as they are within a cluttered environment, or use them in parallel. All right, that gives you an idea about the physical intelligence side of things and how we can build robots. In the next, I guess, 20, 25 minutes, I want to talk about the computational side of things, because that is, now that we can build robots that can operate in a way we like, is an even harder problem, I would argue. At this point in time, I feel like it's easier to build a continuum robot than to control it properly. I'm going to talk about state estimation mostly, and then also talk about some of the joint work we did with Oren on environment interaction strategies. So a continuum robot is great. By now, you have seen a couple of them moving around, and this is an easy, I guess, thing to do. But when you look at it from a, I guess, computational standpoint, you would like to obviously understand, what does my input cause of a shape, and how is this shape influenced by external forces and stuff. So what we really look for is not only where is the tip pose of our robot, but we essentially would like to know, where's this red dotted line? What is the center line of this robot? So we would like to express its shape. And we would eventually want to know the shape under any circumstances, any external loads, internal loads, external interactions with the environment, gravity, so on and so forth, depending on material properties and so on. So that becomes a pretty challenging problem, because we cannot just use conventional robot kinematics and dynamics formulations. And the first question that you have to ask yourself is, well, how can we represent the state of a continuum robot? And so deciding for a state representation, meaning that backbone curve parameterization, there's multiple ways we could go about it. A very common one is approximating the shape with lumped parameters. Usually we use constant curvatures. That's the simplest way to describe the shape, in that you approximate it as a series of tangential constant curvature arcs, and each arc is then characterized by its curvature kappa, the bending plane phi, and the length of the arc. Another possibility to be a bit more descriptive, if the robot is also subject to external loads, the shapes may not be constant curvature. We move to modal functions. We have seen that Euler curves are a very great representation because you have that, I guess, change in curvature, which is much more reflective of contact. Or you use some other sort of modal function, polynomials, you name it. Many of those have been investigated for continuum robots. But ultimately, and in the ideal case, you would really like a variable curvature or distributed state representation where you parameterize the whole robot by its arc length s, so from the base all the way to the tip. And then you use the strains, the bending strains, as well as the shear and elongation. So a 6 vector that travels along that arc and pretty much tells you what is the pose, so the position and the material orientation at any point along this robot. And that is the ultimate representation. But as computer scientists, you can probably already appreciate you have efficient to compute, low parameter representations on the left. And on the other hand, you have these high model fidelity, almost infinite number of parameters on the right-hand side, which pretty much put us at a trade-off. On the one hand, we are less robust to unmodeled effects like gravity, external forces, but pretty efficient to compute. And on the other side, we have this high fidelity, but also high requirements in terms of sensing to move these models into the real world. So using a state representation that we picked, we can then go into a forward modeling, meaning input is the tendon tension or tendon displacement on the back end, eventually knowledge about external forces. And then we can take a pure physics-based first principles approach, use a piecewise constant curvature framework, which relies on this modal functions, some limited state representation to compute the shape. And as a rule of thumb, the accuracy we can achieve, if it's well calibrated, is 5 to 10% with respect to the robot length. That's usually how we express error here. The state-of-the-art model uses mechanics. So we are actually using elasticity theory and representations of beams from mechanical engineering, like Koszrad rod models, to derive kinetostatic models, meaning to fully understand and describe internal moments and forces as well as external loads among the whole body with all the material properties as the robot experiences elastic strains, usually Hooke's law, in order to determine how developed stress is directionally proportional to the strain the robot experiences. And then with this high level of complexity, we can actually achieve quite high accuracies if it's well calibrated and the system is identified well. We can get down to this 1.5 to 3% with respect to lengths. Meaning, if you have the 30 centimeter long robot, you get an error just model based about 4.5 millimeters at the tip without sensing. So that's quite fair, quite remarkable. Obviously not in the same ballpark as with industrial robot, where you usually go into sub-millimeter accuracy. We've also taken on a learning-based approach, looking at how a vanilla feed-forward neural network will perform. Often our issue is data. In continuum robotics, most labs have their own prototypes. There's no standardization. So if we collect a data set, it's valid for our robot, but it's not really transferable. It's one of the challenges we face in continuum robotics. However, for this robot we see here, we have collected a series of data points, meaning the input parameters, actuator values versus position of the tip and various points along the robot body. And we could see that the, I guess, generalization works really well. So we could get the physical modeling error down to below 0.5%. And I think that's the most accurate I have seen so far, at the expense of learning-based methods. Need to do that for every robot, so on and so forth. Anyway, bottom line is we can model the behavior of continuum robots very well to date. I think the continuum robotics community has has converged quite a bit to these piecewise constant curvature versus Cosrod-Rod model, eventually offset with some learning. Using this forward model, we can already do quite a bit. We can invert the model using finite differences and then go into a pretty much standard teleoperation control scheme where the input by the leader is some desired velocity at the end effector or at the tip, and then we can use a model-based controller to servo the robot to the desired to that desired velocity, and then we can pretty much close the loop without any actual sensors, but just by the human eyesight and human judgment. And so we have also applied some model predictive controllers to keep the robot within a conformed environment. Like here, it would automatically not get out of this allowed region, which makes teleoperation for these robots relatively intuitive. And we have seen great success with this teleoperation scheme as the continuum robotics community immersed, that there are many commercial medical continuum robots to date that are pretty much using this model-based design teleoperation in order to make meaningful contributions to patient care. We have these catheter steering robots where you have multiple catheters that are nested inside each other and then controlled from outside the room to prevent radiation exposure for the physician. We see robot bronchoscopy systems, for example, this treating this bronchi that I mentioned earlier, doing the biopsy of suspicious tissues. We also see single port systems that use this like I guess shape, continuous curve instruments to gain better triangulation in space within a confined surgical environment. And there's also some recent work on more for prostate surgery where you go through the natural orifice and using these small continuum robot tools can do some laser resection of benign prostate situation. So this is great. You could argue continuum robots pretty much found their way into medicine. And this is a big portion of the work we have been doing over the past, or in the past decade, or pretty much since I moved to Toronto. We have been diverging a bit because I believe in medical continuum robots there's not that much needed in terms of design and maybe also not the need for so much autonomy. But as we're looking into other applications, we are facing new challenges. The next generation of continuum robots will probably find applications outside of medicine where we do not necessarily need the human in the loop. So we will need to come up with better ways to sense and reason about the state of our robot. We cannot rely on a physician visually observing its environment and I guess correcting for any uncertainties. So we will need to navigate autonomously through the environment with limited and noisy information, like in this turbine inspection scenarios or pipe inspection scenarios. And the biggest challenge we have been facing here is pretty much thinking about from a measurement. Let's assume we measure these 3 points in space. What is the actual robot state from this very limited observation? So your model will probably tell you the robot is somewhere here. There's maybe some information you have at your site. But then what is the actual robot shape and state at any point in time? And in this dilemma, measuring the robot state, you can obviously use discrete measurements and do some regression and try to find a shape that suits. Many have been doing this, but what has been really remarkable is a collaboration that we have with Tim Barfoot here at University of Toronto. And what Tim found when he heard one of my talks is that there is this analogy between the continuous trajectory of a mobile robot and the continuous shape of a continuum robot. And so that's an exciting revelation we had. So on the one hand, we have a continuous trajectory. So imagine this mobile robot moving with respect to time. Its state, it's usually its pose. It's a homogeneous transformation matrix. And then you see the generalized velocity, usually expressed as a twist in the Lie algebra. And then the differential kinematics, it's pretty much the time derivative governed by the twist using the exponential map in the Lie group. And so on the continuum robot side of things are actually quite comparable or analogous. Here, recognize it's not the shape is not expressed with respect to time yet, but here it's only expressed with respect to arc length. So from the base to the tip, pretty much similar to here with respect to time, just with arc length s. So here we have the position and orientation at any point along this robot as well. But here we don't have the generalized velocity, but we have the generalized strain vector, which is pretty much the spatial analog of the generalized velocity, but for spatial deformation. So rather than the temporal evolution, here we are describing the pose changes along space, meaning bending, twisting, shear, elongation. And so then the kinematics is expressed as the derivative with respect to arc lengths. And here we have the generalized strain vector and its exponential map. And so we can determine the kinematics. And so this analogy pretty much allowed us to tap into state estimation for mobile robots and this rich methodology and repurpose and reformulate those methods for continuum robots. And Tim has been remarkable in identifying this analogy. And then it has been Sven Lilge, who did his PhD, co-supervised with Tim in my lab. And this is Spencer, who is now following up on this great work. And I want to tell you a little bit what we did here. So we use Gaussian process regression to estimate the state, meaning we create a prior distribution, a zero mean Gaussian process on the strain derivative with respect to the robot arc lengths, meaning the internal material stresses. And this prior then makes no assumptions about forces that are acting on this continuous body and favors configurations with minimum internal stress, which is also what a physics or mechanics-based model would do, energy minimization. So we usually assume that we know base, that we have some strain boundary conditions. And then here I'm just showing you the prior mean and some random samples for this Gaussian zero mean prior. And then we formulate, oh wait, I should mention that. So it's zero mean, and then here we have the power spectral density matrix, which is the continuous version of a covariance matrix. In our case, it's usually diagonal, can be used to make the prior more or less restrictive in certain degrees of freedom. So it's conceptually tuning the robot's compliance. Then we formulate this as a factor graph. We have prior factors and measurement factors. We define squared error terms or cost to evaluate how close is the continuum robot state to the prior assumptions. Then we assume we have some noisy measurements which relate discrete states, and they are also expressed as measurement error terms in this formulation. And finally, in this process, we can determine the most likely continuum robot state and its posterior distribution given both the prior and those measurement factors, and the respective error time terms would need to be trade-off against one another. This is formulated as a batch optimization problem, which seeks to minimize the overall occurring cost and maximizes the likelihood of the posterior while involving all the discrete states. And this procedure is as a maximum posteriori estimation. So the posterior distribution would then give us the mean robot shape and also the covariance at any point in time. And as it's a batch process, we can also interpolate between the discrete states. And this works remarkably well. It's pretty much repurposing what Tim's lab developed for mobile robots. And here we see an example. So here we have the actual robot, and on the left-hand side, we have the state estimation. This is using pose measurements, 3 pose measurements. And you can tell that there's quite some agreement in the state estimation. We evaluated the error in simulation and found that it has about 1% with respect to length, which is quite well. Sven was also able to extend this to multi-continuum robot systems. Here we see 2 coupled continuum robots where we only take one measurement at this joint location in the center here, so 1 position measurement. And then we see the state estimation performing on this measurement over here. And on the right-hand side, you get an idea about the computation time. So most of the time, we stay below the 10 millisecond domain, but you will see as the video progresses that at some portions we are peaking up. But in general, we can stay below 100 hertz most of the time. Sometimes there are these little peaks, which are a little slower. So these are all quasi-static. We don't make use of previous states yet. This is the work that is now continuing now that Sven finished his work. Spencer is moving on to space-time continuous state estimation. So not only quasi-static from one measurement estimating the state, but truly looking at the temporal evolution as well. So here is just some early results that he got recently. So this is the simulated robot that he's basing his study on. And then he can determine the continuous space-time shape using, for example, here it's two pose sensors. You see the uncertainty at the location of the sensors is as expected low. There's one sensor in the middle and one sensor at the tip. And then in between, we interpolate between these discrete states. If we only have a strain sensor at various locations along the robot, we get this performance. So obviously, due to integration, we get a higher uncertainty at the tip of the robot. And ultimately, if you combine multiple sensors, for example, two pose sensors, one strain sensor, you would get a much more certain estimate about the robot shape. I'm excited about this work. It's not a major publication yet, but I figure I'm going to show you these early results to make a point on that. I think we're very close to being able to do state estimation in a way that it's ready for being used in actual applications for autonomous navigation in clouded environments. All right, so state estimation is a work in progress, going pretty well. Another aspect that we're tackling, and that's the work we did with Oren, I'm only going to touch briefly on, is that in the majority of robotics, we have pretty much always tried to avoid obstacles. Any rigid robot motion planning scheme pretty much looks at do not make contact with the environment, giving some guarantees on not actually touching an obstacle. And that has been for the longest time the paradigm. But this doesn't really make sense because we seek to empower robots to embrace contact. So even though there is a huge push in robot manipulation, on the one hand, to make this contact, there's also, and even more importantly so, in soft and continuum robotics. So often we point out that continuum robots are compliant, safe to interact, but it's interesting that most of the literature is using continuum robots in free space, not tackling the challenge of contact, or they are just not leveraging contact at all and trying to do it in a obstacle avoidance scheme. And so with this problem, I was making this call to the community that Oren was responding to, and that kicked off our collaboration. And I'm really proud that we are, I think, the first that tackled this motion planning paradigm shift, leveraging contact with the environment to gain additional motion capabilities in continuum robots. And this contact-aided navigation work was mostly done by Priyanka Rao. She finished her PhD last year and was greatly helped with supervision by Oren. And we may have this great publication that she just recently showed at ICRA. And I want to give you just a little bit an idea about the challenge and talk only briefly about what we did so that we have time for questions later. So contact-aided navigation sounds great, but it's actually quite challenging because in continuum robots, temporal information matters. That is the sequence of motion and contact establishments. I want to draw your attention to this figure up here on the left. So this is a continuum robot, and we are assuming it can only extend and bend. And here to the left, we see if we applied 3 extension actions first, 1, 2, 3, the robot would be up here. And then we apply 2 bending actions, meaning we displace the tendon a little bit to pull the robot to the side. So after these 5 actions, the robot would be positioned like this as it established contact with the obstacle on this side. On the other hand, if we change the sequence, we did the bending first, so we bend the robot over and then extend, you can tell the final robot shape is quite different, though from the actuation side of things, the actuation parameters are identical, right? So the actions are the same, so the joint representation is identical. So that makes this motion planning problem actually quite hard. And doing contact implicit motion planning to a target pose in an environment while also inferring necessary contact interactions without predefined contact modes is something that hasn't been tackled before. And so Together with Oren, we developed this search-based motion planner on a graph that we pretty much navigate using a heuristic that estimates the distance to the target by iteratively propagating series of mutually tangent constant curvature arcs. And we were able to showcase that that works actually pretty well. And it is the first motion planner of this kind. The next challenge is moving this to 3 dimensions. It works well in the plane, but I guess a computational bottleneck is pretty much the contact model. And if we think about dynamic environments, this is going to be a major computational challenge. And I hope we find the students soon to tackle this together. And it's probably going to be a combination of state estimation with planning that we're going to look at here. Before we're wrapping up, I would like to mention the Open Continuum Robotics project that Oren was mentioning. For the students that are listening to the talks, or maybe even to some of the PIs here, if you're excited about continuum robots or feel like I want to know more, that has actually become a bit easier, I hope, because there is quite an entry barrier if you want to get into continuum robots. You cannot buy continuum robots off the shelf. There is no textbook. There is limited material available online. If you have a student that wants to get started, they usually have to read hundreds of papers to get an idea of where the community sits. And that led us to create the Open Continuum Robotics project, opencontinuumrobotics.com, to lower this entry barrier and to mobilize continuum robotics knowledge. So I have been leveraging continuum robotics course material that I created, pretty much discarded my idea of writing a book and decided to create this blog to have experts from the community and myself contribute to entry-level material for the educated roboticists wanting to know more about continuum robots, but also for continuum robotics graduate students, postdocs, researchers that want to keep up to date with research advancements. We also provide some of the first data sets in the field. We have developed some software tools and are also providing hardware, CAD files, assembly instructions, bill of materials to empower the non-mechanical design prone labs to also be able to build their own robot, hopefully. And so this pretty much became a hub for the community, and I've been really happy to also have Oren contribute and write about motion planning for the community. It's been really well perceived posts, and it's generally quite a good effort. Okay, I'm going to stop sharing for a second because I realize I did not share sound. Wait, oh, I don't need to unstop. Okay, never mind. I'm going to show a video without sound. This I'm really sorry about. My Zoom has updated and I have to, would have need to, I guess, exit Zoom to enable sound sharing. So let's just watch it and enjoy. This is the vision for continuum robots moving forward. Robots being in the human body, entering through these natural orifices, eventually doing very delicate surgeries. And then leaving the human and also being useful in all sorts of other applications. And with that, I have to say I'm fortunate to work with a bunch of bright students and collaborators. This is a couple of them. I'm really thankful to being able to work with so many bright minds. It's their research that I'm just able to present, not mine. And then I'm also thankful to the Canada Foundation for Innovation and the Natural Sciences and Engineering Research Council of Canada for sponsoring our work. And with that, I'm happy to answer any questions that you might have, and thank you for your attention.
Thank you for this very inspiring talk. I have a bunch of questions, but since we know each other, I'm going to hold back and let other people ask. So the stage is open, and if not, then I'll bombard you.
How do you choose an optimum distance between disks and the ratio of disk diameter to distance between disk centers?
A very good question. Depends on the tasks, on the amount of forces we'd like to exert. Obviously, the smaller the distance, the less bending moment you can apply. So that limits the motion ability. So it's pretty much a trade-off of what you want to achieve. If the diameter, like the 7 mm I showed in the beginning, is pretty much on the smaller side of things, 6 mm eventually, but that's pretty much at the low end. And then on the upper scale, it's mostly how heavy is the body going to get. So you have seen some of the larger scale for the inspection jet engine or aircraft wing. We have larger diameter, but there we also use mostly 3D printed, very lightweight material so that the body itself doesn't become too heavy, because withstanding their own weight, withstanding gravity becomes an issue the longer the robot gets. So it's a real trade-off that we have to make. And there's no recipe, I fear, yet.
Thank you for a great talk.
Thank
So
you.
I am going to ask, because it's a follow-up question about the literal elephant in the room, which is not miniaturizing them, but what do we need to do, or what are the challenges to make these long continuum robots, where gravity becomes an issue, actuation becomes an issue, payload becomes an issue. So all of the problems, I
Friction.
think miniaturizing, you guys solved all of the problems.
Yeah,
And
miniaturizing at a small scale, like 30 centimeters, everything patient, perfect. That's why on the medical side of things, things are easy. In medicine, we also have very long continuum robots when you think about catheters, but they have a different actuation paradigm. Even though you may have a tendon at the back to do some bending at the tip, you are enclosed in the vasculature. So you are enclosed in an environment which provides steering means. And I think that's probably going to be one of the tricks you're going to do in cluttered environments is make good use of the environment in order to gain steering capabilities with limited actuation. But still, friction is going to become an issue, right? The longer the body is going to be, if we're going to stick with tendon actuation, this is going to be a true challenge. What I find really exciting, it's something that we don't work on ourselves, are these eversion-based robots or vine robots that do actually use air pressure to do extension contraction, but they have more issues with steering. They can become very long, but yeah, I think the community hasn't really converged yet, but that is an elephant in the room that I hope with some smart state estimation, smart motion planning, smart interaction with the environment, smart design, we hopefully can tackle.
do you think that means that we require a paradigm shift, or just do everything that you guys do just better?
No, I also think paradigm shifting a little bit. That some of the work we're doing with the trying to use multiple continuum robots supporting one another, or maybe anchoring in the environment to gain stability and to also reduce some of the actuation friction. I think it's going to be both on the embodiment side, on the physical side of things, making smarter designs that would alleviate some of the pain. And on the algorithmic side as well, is then it becomes a question. If you think about, you have this primary robot that may eventually move into a cluttered environment, then you have this supporting robots coming from the side, eventually holding it, supporting it. And then you have to also, this becomes a much more interesting planning problem. Like, where are good locations to hold on to? What is the coupling going to look like? What are good environmental interaction strategies, right? Which obstacles to interfere with? Where can I maybe brace the environment or lean into? Where could I maybe, I don't know, throw out a hook to hold on to the environment to go a different way? I think it's going to serve both our careers well.
I think I have a follow-up question on that, maybe not. Did you also consider settings? Because I mean, I saw first of all, it was a great talk, very exciting domains. I'm always envious at Oren for having such exciting examples. I was wondering whether you were considering also settings in which you need to consider the trade-off in a principled way, considering the trade-off between collision avoidance and the ability to exploit the environment for certain manipulations?
Not yet. That's, I think, next frontier.
Okay, great.
I have some other question. So you mentioned in your presentation, which is great actually, some collaboration with Tim, right? Tim Barfoot. So was it a batch calculation, or did you guys explore incremental aspects of this paradigm?
No, it was mostly batch. He would be much more proficient in explaining the process. But yeah, it was his batch optimization that he did for mobile robot continuous time trajectory estimation. I think it was his 2015 paper that pretty much laid the foundation for this work. And it was, we could almost use the math one-on-one.
Very nice. Thanks.
I think we have time for one quick question, or we can wrap it up.
I
Anyone
have a
else?
quick question. So you were saying when you talked about the state estimation, you gave the two examples of pose estimation with a external tracker or something like that and strain gauge. What about measuring so these are all cable driven. What about using the cable length as also an estimate? Did you try to somehow fuse that information as well?
Yes, that we didn't do it, but that would certainly be then in a more informed prior, I guess, if you use the actuation information. We didn't do it because we made quite some use of sparsity, and that would have probably increased some of the computation costs, but it's definitely on our agenda to look into this. I also have a postdoc that recently started, Tongxia Zheng, and he is also looking at if you have just measurements at the base or at the tip, actually wrench measurements. He can also do a quite nice informed approach to estimate the state, which is more a more informed model. But yeah, certainly these are future directions and certainly make sense.
Okay, great.
I think this is a good time to thank Jessica again for the great talk, especially given that it was this early in the morning for her. So thanks again for waking up and for the talk.
Thank you so much. I appreciate it.